Off the coast of Japan in November 2023, 3 V-22 Ospreys were preparing for what should have been a routine training mission. After a refueling and maintenance stop in Iwakuni, 2 of the 3 Ospreys took off to practice refueling with a C-130 and perform a free-fall water jump, with the 3rd Osprey trailing 1 hour behind in support. The 2 leading Ospreys, Gundam 21 and 22, carried 23 crew members, 15 in Gundam 21 and 8 in Gundam 22. 40 minutes into their flight, Gundam 21 received a message from its sister aircraft.
We have 3 chip burn advisories, but plan on continuing the mission. Copy.
10 minutes later, Gundam 21 saw Gundam 22 start to head east, deviating from their planned southbound route. Right after, Gundam 21 received another message.
We've got chips. Do you need support? Negative. Continue the mission.
Gundam 22 was now heading east towards Yakushima, a landing site just 15 minutes away, despite the availability of closer alternatives. As they approached, they initiated communication with Tower Control.
This is Gundam 22. We are requesting to land on runway 32. Over. There's traffic on the runway. Is this an emergency? Affirmative.
This was the first and only mention of an emergency given by the crew. Waiting for the runway to clear out, the Osprey did one last right turn loop before performing its landing approach at 300 meters over sea level. Just 2 minutes before landing, the left nacelle caught on fire. 6 seconds later, and the Osprey went through a hard roll, and it fell from the sky and impacted the water. What followed was the immediate grounding of all Japanese and American Ospreys. A search and rescue mission began right away and lasted for 48 days. While some remains washed ashore, the main hull and its 8 crew members were found a month later by divers, 30 meters deep near the crash site. The Osprey is an impressive machine, a hybrid of helicopter and airplane. In theory, it overcomes many of the limitations of helicopters by flying at speeds over 200 knots and covering greater distances, all without needing the long runways required by conventional planes. But this crash only adds to the list of fatal accidents involving the aircraft. So let's take this opportunity to look deeper into the V-22 Osprey. Is it safe? How does it work? And how did they figure out what happened to the Osprey that crashed in Japan? The inception of the Osprey came out of necessity. In 1980, in the midst of the Iranian Revolution, a cascading sequence of events led to a hostage crisis, where a group of Iranian militants stormed the US Embassy in Tehran and took 54 hostages. To extract the hostages, the US needed to use heavy-lift helicopters. The RH-53 Sea Stallion offered a way to approach the embassy from above to make extraction easier. But Tehran was too far outside the range of the Sea Stallions that were stationed aboard the USS Nimitz, 96 kilometers outside the coast of Iran. Sea Stallions, like all helicopters, have a limited range, since hovering consumes fuel needed for forward flight. They also face speed limits. As they travel forward, one side of the rotor moves forward while the other retreats backwards, meaning, with the relative velocity of the helicopter added, one side of the rotor is traveling faster than the other. Eventually, the helicopter can't travel faster, as shockwaves and flow separation will occur on the advancing blade tips. Despite being one of the fastest helicopters, with a top speed of 360 km per hour and a range of 1,000 km, the Sea Stallion still couldn't cover the nearly 1,400 km between the Nimitz and Tehran. The plan therefore included a refueling stop for 8 helicopters in the middle of the desert using 3 C-130 cargo planes. The location was dubbed Desert 1. However, this plan quickly descended into chaos. As the first C-130 landed, a bus filled with 43 Iranian civilians was seen approaching. The soldiers stopped the bus, and as they were unloading it, a fuel truck was seen approaching from the other side, and it wasn't slowing down. With the mission at stake, the soldiers began shooting at the fuel truck, which erupted into a giant fireball, illuminating the mission location for all to see. Further south, the squadron of 8 Sea Stallions, codenamed Bluebird 1 through 8, were already facing challenges as a sandstorm had formed between them and Desert 1. A warning light flashed in the cockpit of Bluebird 6. Something was wrong with one of its blades. The blade rotors were hollow and filled with pressurized nitrogen. This pressure was monitored to detect cracks in the rotor blades. When Bluebird 6's light went off, it signaled that the rotor was compromised and they needed to land immediately. The crew of Bluebird 6 abandoned the helicopter in the desert and transferred to another helicopter that had landed to assist. The mission was now down to 7 helicopters. The remaining Sea Stallions pressed on through choking dust clouds, which cut visibility to mere meters. Bluebird 5 then faced electrical failures, leaving the pilot with barely functioning flight instruments. Flying basically blind and unable to locate the other helicopters or assess weather conditions at Desert 1, the crew of Bluebird 5 decided to turn back, unaware that they were just 25 minutes away from clear skies. The mission was left with the bare minimum of 6 helicopters needed to continue. As the remaining 6 approached Desert 1, they saw the giant fireball illuminating their landing spot. The plan from here was to refuel and regroup 92 kilometers east at Desert 2. The sand and the heat had caused too much damage to one of the helicopters, causing its hydraulic system to fail, pushing the number of functioning helicopters below the planned mission abort threshold. Amid the chaos, with civilians nearby and a massive fire raging at the heart of a covert mission, the commanding officer made the difficult decision to abort the mission and retreat. This mission failure highlighted the need for a new heavy-lift aircraft that could have made the 1,400-kilometer trip and was also capable of hovering for extractions. Enter Bell helicopters, which had been experimenting with hybrid aircraft since the 1950s. At the time, there wasn't much interest in an aircraft that was less efficient than a helicopter at hovering and less capable than an airplane in flight. But with NASA's support, Bell developed a vertical takeoff and landing demonstrator, resulting in the successful testing of the XV-15 by the 1970s. When Operation Eagle Claw failed, the Marine Corps decided to give Bell the go-ahead to develop the XV-15 technology further into the V-22 Osprey. The next 2 decades saw the concept refined from a testbed to a functioning aircraft, with first hover in March of 1988 and a first fixed-wing flight 2 months later. Since then, Bell and Boeing have provided 3 Osprey variants to the US military: the MV-22 for Marine Transport and Rescue, the CV-22 for Air Force Special Operations, and the CMV-22B for Navy Replenishment. The core feature of the V-22 Osprey is its unique tilt-rotor system. In helicopter mode, the pilot uses helicopter controls that use a fly-by-wire system to control the actual maneuvering mechanism. The collective pitch of the prop rotor blades enable the aircraft to hover, while roll is controlled by changing the collective pitch for the blades in the opposite directions. Pitch is achieved by tilting both rotors in the same direction, and yaw is controlled by tilting the rotors in opposite directions. This precise control allows the V-22 to hover, take off, and land vertically with ease. When transitioning to airplane mode, the V-22 tilts its rotors forward until they function as traditional propellers, providing thrust for forward flight. In this mode, the aircraft's control surfaces, including the ailerons, rudders, and elevators, take over the primary control functions. The transition between helicopter and airplane modes is controlled by a small knob on the pilot's controls. Pilots are trained to use only a few specific tilt-rotor angles to avoid complex aerodynamics. With just their thumbs, the crew can adjust this dial, which sends a signal to the fly-by-wire system. In helicopter mode, the nacelles tilt between 80 degrees and 97.5 degrees, usually staying at 90 degrees. Mechanical stops at 0 degrees and 97.5 degrees ensure the nacelles don't go beyond these limits. The pilots can make short landings with the nacelles tilted between 90 degrees and 60 degrees. The actual tilting mechanism, located on the edge of the wing, uses a hydraulic motor to turn a long telescoping screw. One end of the screw is attached to the wing, and the other to the tilting nacelle. As the screw extends, the nacelle tilts upwards. The V-22's nacelles rotate independently, so precise control systems are crucial. Any small difference in the nacelle's position during hovering could cause a catastrophic crash. The prop rotors serve a dual purpose, generating lift in helicopter mode and providing thrust in airplane mode. This blend of airplane propeller and helicopter rotor functions is what gives them their unique name, prop rotors. Their dual function is clear by simply looking at them. The C-130 has propellers that are 4 meters in diameter, whereas the Sea Stallion's rotor has a diameter of 21 meters. The V-22 prop rotor sits somewhere in the middle with 11.6 meter prop rotors. Another aerodynamic trade-off with the V-22 is in the twist of the prop rotor blades. Helicopter blades usually have a twist of around 8 degrees, but the V-22's prop rotors also need to act as efficient propellers when the incoming airspeed is much faster. To handle this, the prop rotors have a 47-degree twist. While this improves efficiency in forward flight, it comes at the cost of reduced hover efficiency. Hover efficiency is measured by disk loading, the ratio of the aircraft's weight to the rotor's circular area. A rotor works by pushing air downward to generate upwards lift. For helicopters, it's easier to create this lift by moving a larger volume of air slowly rather than a smaller volume quickly. The V-22 is heavy and has a small rotor, resulting in an inefficient hover with a high disk loading. This high disk loading means that to hover, the Osprey needs to push down more air at faster speeds than a helicopter. For a helicopter, this downwash is normally around 60 knots. Hurricane winds are around 64 knots, and the V-22 has a downwash of 80 knots, which can make ground crew operations a little difficult. The Osprey's tilting nacelles and intricate mechanics rely on a network of 5 gearboxes and a complex shaft system to function, which comes at a high risk. Every component is an extra point of failure. So, how does this system work, and what exactly went wrong during the training flight in Japan? The propeller gearboxes of the Osprey are nearly identical, with a key difference in the right gearbox, which has one less gear to enable the prop rotors to rotate in opposite directions. The aircraft is powered by 2 Rolls-Royce turbines and an auxiliary power unit that assists in rotating the entire wing assembly parallel to the fuselage, a necessary feature for storage on an aircraft carrier. In helicopter mode, even a slight difference in the rotation of the V-22's prop rotors could create significant asymmetrical forces, leading to instability and large roll movements. To prevent this, the prop rotors are linked by a shaft, like in other dual-rotor helicopters. But unlike traditional designs, the V-22's rotors are not linked by a straight line. They are connected through its wings. From above, you'll notice that the V-22's wings are swept forward. This isn't typical for planes, but this isn't for aerodynamics. The forward sweep gives the large prop rotors enough clearance to avoid colliding with the wings. A straight wing would require the heavy tilting nacelles to be pushed further out, creating more structural and aerodynamic challenges. Viewed head-on, you'll also see the wings tilt upward slightly, by just 3.5 degrees. This subtle dihedral angle not only adds stability during airplane mode, but also ensures that when the wings are folded parallel to the fuselage for storage, that the nacelles have enough clearance to rotate smoothly into position. So, instead of one continuous straight shaft, the V-22 shaft is split into 6 sections to handle the 13-degree wing angle and to share power between the engines, allowing the V-22 to be powered by a single engine if necessary. But the nacelles are not rigidly fixed to the wing, so an extra gearbox is needed. The tilt-axis gearbox transfers power from the interconnected shaft to the prop rotor gearbox, no matter the angle the nacelle is positioned in. The gearboxes need oil to keep everything running smoothly, reducing friction and keeping the gears meshing properly. The oil also doubles as a way to monitor the health of the gearbox. As gears wear down, they shed tiny, harmless particles called fuzz, especially during braking. The real problem comes when failing gears produce bigger metal chips. We need a system to detect and remove these chips without opening the gearbox and replacing the oil. A small magnetic detector can be placed in the oil flow to attract the metallic chips. It has 2 open contacts that close when a metallic chip touches them, acting like a switch. A pulse of electricity is then sent through the chip to melt it. Bigger chips need more energy and pulses, and if a chip is too large to burn off, the system alerts the pilots. It was this chip detector that was triggered in the latest Osprey crash. Each prop rotor gearbox has 3 separate chip detectors that all work together to collect and burn chips. From the conversations with the tower and the other Osprey, the investigators knew that there was a problem with the chips, even before recovering the aircraft. They just didn't know what part had failed. Once recovered from the ocean, the flight log filled in the gaps of information left by the conversation with the tower and the sister Osprey. In the span of half an hour, the system reported that it had successfully burned 5 chips. Protocols say that one alarm is merely a warning, but once 3 chip burns occur, the crew should land when practical. However, landing is ultimately at the pilot's discretion, as other factors may affect the urgency of the alarms. In this case, the crew believed the alarms were caused by a faulty chip detector. 3 minutes after the 5th chip burn, the system issued a warning that a chip could not be burned. Protocol at this stage requires the crew to land as soon as possible if no secondary effects are observed, or to perform an immediate landing or control ditching if there are signs of overheating. This is when the crew decided to divert. For unknown reasons, the crew chose to land at an airfield 15 minutes away, despite closer and suitable options being available. Voice recordings revealed no sense of urgency, and once the pilot made the decision, there was no further discussion about the choice. Sadly, as the Osprey came into final approach, the left nacelle caught fire, causing a catastrophic failure of the propulsion system. From that point forward, the crew could not have done anything to save the aircraft. After the aircraft was recovered, tests on the left nacelle found no fuel or hydraulic contamination. The 3 chip detectors were removed, and they were all surrounded with debris. After they were cleaned, the investigators confirmed that they were functioning properly. The gearbox failure was evident from a broken gear in the prop rotor gearbox, with the drivetrain showing severe wear and gear teeth ground nearly smooth. After this crash, the Osprey fleet was grounded for months. Limited flights resumed in March, but the aircraft still isn't performing its full range of missions, including carrier operations. This crash was the 4th since 2022, with accidents involving previously unseen mechanical failures. For example, in June 2022, a clutch failure caused a crash that killed 5 Marines. The clutch had worn out faster than expected. In that incident, a rare dual clutch engagement left the pilot unable to save the aircraft. This string of crashes has reignited questions about the safety and reliability of the V-22 program. Since its inception, the V-22 has been seen as an unsafe vehicle, even earning it the nickname Widowmaker. Like any groundbreaking technology, the introduction of the world's first tilt-rotor aircraft involved a steep learning curve. The large capacity of the V-22 means that these accidents carry a larger risk with the added personnel on board. In 2000, during a training exercise, one V-22 Osprey descended too fast in helicopter mode and crashed, killing the 19 crew members. When any helicopter descends too quickly, air starts flowing upward near the hub area where the blades are travelling slower, causing the center section to stall. As this happens, vortices form near the center of the rotor that can cause a sudden loss in lift. While no mechanical failure was the culprit of this incident, after the investigation, the V-22 was limited to descending at a maximum of 4 meters per second. Just a couple of months later, a faulty hydraulic line caused another crash, adding 4 more deaths. These 2 back-to-back accidents severely tarnished the program's reputation and has led to a lasting negative public perception. But what does the data say? Since 1991, there have been 25 incidents involving the V-22. 9 were caused by pilot error, 10 by mechanical failures, 2 were a mix of both, and 2 are still under investigation. This has led to the unfortunate death of 58 service members, but how does this compare to 2 other helicopters, the Sikorsky H-60 and the Chinook H-47? Since its debut in 1979, the H-60 and its variants have had 390 incidents, resulting in 970 deaths. 60 of those happened in the last decade, which is 2 more than the V-22 has caused over the past 30 years. The H-47 has historically had the Army's highest death rate per incident. Between 1966 and 2005, 238 lives were lost in 10 non-combat crashes. But in recent years, the H-47 Chinook has had huge improvement in safety, with 47 incidents and no deaths between 2016 and 2020. Simply comparing the fatalities does not account for how many aircraft have been built and how much they were flown. In accidents per airframe, the V-22 fares quite well, with only 0.06 to 5 incidents per aircraft, compared to 0.75 and 0.11 for the H-60 and H-47. But if you account for flight time, the V-22 has more deaths per 100k hours. This data shows a couple of trends. Larger aircraft, like the V-22 and H-47, tend to have higher death rates per incident because they can carry more people, increasing the risk per crash compared to smaller aircraft like the H-60. And more complex aircraft usually see a spike in incidents early on as problems are identified and fixed. But these issues tend to decrease over time as the aircraft matures and systems are improved. These comparisons are not intended to put the V-22 above other military aircraft or dismiss its safety record. No aircraft is without flaws, and every accident is a stark reminder of the risks faced by service members. However, the data clearly shows that the V-22's safety record is not an outlier. Crashes don't always tell the full story of why certain planes were deemed unsuccessful, and no other plane exemplifies that more than the Concorde. The story of the Concorde is fascinating, and it's a story many people get wrong on YouTube. But we have curated all the best aviation channels in one handy place: Nebula. When I search for videos about the Concorde on Nebula, this is what shows up. You can watch all of these ad-free, with fantastic videos from Mustard, Wendover Productions, and Bright Sun Films, with 2 of these videos being exclusive to Nebula. That's what this little plus symbol means. This denotes supplementary content exclusive to Nebula. You can go to your library page, which acts like the subscription feed on YouTube before they broke it, and sort by plus. And here is all the plus content from Real Engineering and our sister channel, Real Science. Hours of additional interview segments and loads of documentaries that didn't quite fit into our niche of engineering here on YouTube. You can also sort by originals, which are high-budget original programming funded entirely by Nebula with your support. And here, you can see even more documentaries made by us that are exclusive to Nebula. Logistics of D-Day, the Battle of Britain, and Real Science's Becoming Human series. And we've plans for even more original series this year. This is what Nebula is all about, giving monetary support from subscribers directly to creators. I just completed our 2024 financial sheet, and last year we spent over $1.1 million on production across Real Engineering and Real Science. And when you look at the animations across both channels, you can see why. This is expensive work. Most YouTube channels don't invest this much money into production quality for a reason. It's highly risky, and some videos just make a loss. Nebula's consistent funding helps us stay afloat and keep bringing you the best videos we can make. And this is true for every creator on Nebula. Creators like Tom Nicholas, who recently released Boomers, a documentary detailing how the baby boomer generation managed to amass so much wealth and power and how it's affecting our world. And 2025 is set to be Nebula's highest budget year ever, with even more money being funneled into original programming. So if you want all of that and watch my videos ad-free on Nebula, you can get 40% off the year plan at just $3 a month. And what's even cooler, if you like it and want to share it with your friends and family, once a month, subscribers can share guest passes that provide 1 week of free access to Nebula, and they don't even need to provide any payment method. So they don't have to worry about a sneaky subscription payment being charged when they forget to cancel. Because we want to build a business you want to support, not one you forget you are supporting.